Hello, my name is Popa Stefan, and I'm student at Transylvania University, Faculty of Electrical Engineering Computer Science, specialization Applied Electronics, in the second year. My project name is Hotspot VmodTFT. My project goal is to create a hot swap interface for the VmodTFT module. The objective of the project are: the board sends data to the VmodTFT. The data is the frames of a movie or animation, but I prefer to call it a sequence of related images. The board detects when the module is connected or disconnected. And finally, if the VmodTFT is connected from the board while an animation is displayed and reconnected after some time, it will start the transmission of the animation at the exact same frame when it was disconnected. I use the following hardware: the Xilinx Spartan 6 XC6SLX45 board, which you can see here, the VmodTFT module, and the VHDCI cable to connect the module to the board. The hardware part. The core of the design is the embedded microprocessor microblade. It communicates on the PLB with all the other controllers. I use the VmodTFT controller, interrupt controller, and DDR controller provided by Xilinx. The interruption I used came from the VmodTFT and from timer. The VmodTFT controller contains a module called TFT that has three registry values. Two of them are for coordinates of pixels, and the third one represents the color. To detect when the VmodTFT module is connected or not, I analyze the output signals of the VmodTFT module listed in VmodTFT reference manual. These signals are TP bus busy, TP out, and TP pennies Q. I use TP pennies Q signal. This signal is an interruption, active low, in the moment when the user presses the screen, but its functionality is the same when the module is disconnected. To distinguish between the situation when the user presses the screen and the situation when he unplugs the screen, I also put a condition on the pressure of the screen touch. If TP pennies Q becomes 0 and the pressure of the touch is FFFF, then the screen was disconnected. If the pressure differs from FFFF, then the screen is still connected. So that means that the user touched it. Here you see the block diagram of the hardware. You can see the microblade microprocessor, which is connected through the PLD bus to the other controllers, like the DDR controller, interrupt controller, and the VmodTFT controller. Here we have the timer. Here we have the DDR memory, and this is the VmodTFT module. Regarding the software part of the design, we refer to the C program for microblades. It is an interruption-driven program which realizes the transmission, the graphic part, animation, and the detection. The first step of the project was to develop a C program that displays some images on the screen. To accomplish this, firstly, the images were encoded with another program written in C++ using OpenCV library. The C++ program has a set of 3-channel BMP images as input and the .txt file as output. The content of the output folder consists of a vector for one for red, one for green, and one for blue. The C++ program associates one bit for each component, 0 if the component value is under 128, and 1 if it is above 128. After that, the vectors were copied into the source file of the C program and declared as global variables. In the source code of the project that runs on the microblaze microprocessor, I created a function that displays a frame of a certain type at a given coordinate. After that, I created an animation. This is done by quickly changing different images. The animation that I created has 3 parts, and let me show you the frames of this animation. The first part is a man that works from the left edge of the screen to the right edge of the screen. You can see the frames here. In this part, the frames are square images with height of 80 pixels. To simulate the walking, I had to show the frames at different positions. The second part of the animation shows a stage with a curtain that slowly opens. In this part, the frames are images with height of 256 pixels and the width of 480 pixels. Because the microblaze microprocessor is not very fast and these images are large, the frames cannot change very quickly. The user can observe how the frame is drawn from the upper left corner to the lower right one. You can see the frame of this part of the animation here. The last frame, which is this, the last frame shows that the lights are on. The third part of the animation is a man that appears on the stage, looks at his pocket watch and smiles. After that, the lights are turned off and the curtain is closing slowly. After that, the animation starts with the walking man and so on. The closing of the curtain is made possible by displaying the frames from part 2 in reverse order. The square images of the man with the watch have a height of 94 pixels. Here you can see the frames of a man with the watch. These frames are displayed above the last image of the stage when the lights are on and the curtain is completely open, which means this. These frames are displayed over this image. The user can observe that the frames of the walking man and of the man with the watch are displayed much faster than the opening and closing of the curtain. This happens because these frames are much smaller and the microprocessor has less to work. Although the curtain frames are very slowly displayed, the purpose of the animation as a sequence of linked images is kept. Now I will show you a demonstration of the C++ program that encodes the images. This is the folder where the project is created. These are the frames of the animation. I have the project opened in code blocks, which is the free C++ IDE. Now I will run the program. As you can see, this program loads every image, every frame from this folder and encodes it. The output of this program is this text.txt file, output.txt file. Let's open it with Notepad++. It lasts a bit because it's a very big file. Here you can see all the vectors for the images from the folder. Now let's continue with the presentation. The next step is to detect when the VmodTFT module is connected or not. To accomplish that, I use the break signal of the VmodTFT called Penir Q and the pressure of the touch, excuse me, referred to as the Z coordinate. Finally, when the program detects that the module is disconnected, it adds the frames that should have been shown on the screen in a dynamically allocated queue. This queue is implemented as a simple linked list, dynamically allocated. Adding a frame in the queue is done by adding the frame at the end of the linked list. Extracting a frame from the queue is done by extracting the first element of the linked list. This queue memorizes only the information strictly necessary about each frame, not the entire frame. When the module is reconnected to the board, the program checks if there are any frames in the queue. If there are frames in the queue, then it extracts and displays them one by one until the queue is empty. After that, it will continue to directly send the images to the module. Problems that I have encountered during designing and implementing this project, I have encountered some problems. One of the most important ones is that sometimes when the user plugs in or out the module from the board, multiple interruption signals are sent excuse me, are sent one after another, and the software determines that the VmodTFT is connected when in reality it is not, or vice versa. I try to solve this problem by adding a software filter which counts the frame displayed or added to the queue or extracted from the queue between two interruptions, and if the number is too small, then the program ignores the second interruption. Another problem is that the curtain frames are displayed too slow, but this is the limit of the microprocessor. Why this project? This is my first embedded system project that I developed. I want to learn more about this domain. Since I do not have much experience in using hardware description languages, I chose a primarily software implementation for this project. Although the reason for developing this project is a serious one, to gain experience with new technologies, I decided on this theme with funny animation. Conclusions. The most important conclusion is that creating good graphics and animation on the FPGA is possible. However, I need to say that the insertion of images is not easy. They have to be first processed and stored in a convenient format. Furthermore, I can talk about the limit of the processor. I noticed that once I increase the size of the image over a limit, the microprocessor cannot display these images fast enough. A demonstration of the project running on the FPGA board, you can see this demonstration in the other movie that I uploaded on YouTube. Thank you for your watching.